Hi, I'm Scott, and I'll be talking about my Insight project ContinU, which uses keystroke biometrics to continuously authenticate users on a website. So passwords often aren't enough to keep accounts secure. Nearly 2/3 of adults with social media accounts have had one of those accounts hacked, and this hurts not only their privacy, but also their trust in the websites that they're using. These websites then need to dedicate customer service and security resources, which together amount to about $600 billion globally in cybercrime cost. So to help aid this problem, I developed an algorithm in order to identify users based off of their unique key typing patterns, and a dashboard for a security team at a website to consult to verify user identity. So on the left side of this dashboard, we can see a selection of users from that website, with the users on top having the lowest authentication confidence defined by the algorithm for their recent messages. So if we select one of the users, we can then see a time series on the right for how confident the algorithm was that the recent messages in fact came from that user. And we can see the most recent messages had near 0% confidence and contain text talking about credit card information, which is a bit suspicious. If I select one of these messages, I can then on the bottom compare the keystroke feature statistics of that message in the dots with that user's typical profile shown in the gray shading. And what we see is that there are many red dots, which indicate that features such as the delay time to go from key M to key P were quite different in that message compared to the user's typical activity. So the security team can consult this dashboard when deciding whether or not to block an account. In order to develop this algorithm, I use a data set of 75 users who each typed about 15,000 keystrokes. I split this data into 100 character segments, or what can be thought of as short messages. And then for each message, I computed features of those keystrokes, such as the delay time to get between consecutive keys. So for example, these are distributions showing how long it took 5 different users to go from key W to key A. And we can see that this individual key pair can somewhat differentiate some of the users. But by looking across the feature space, not only at key W to key A, but also other features, we can perhaps identify users based off of their unique profile. So I trained a gradient boosting algorithm on these features with training one model per user in order to differentiate messages typed from that user from messages typed by other users of the platform, so that new messages from an account can be passed into this model in order to determine whether or not they were likely typed by the original user. This model was able to obtain performance of 98% true positive and true negative rates, or in other words, only 2% of hacker-sent messages were falsely allowed through, and only 2% of messages sent by the user were falsely flagged. This performance depended on a number of things, such as the number of training examples we have for the user, how long those messages were, if there were multiple users sharing an account, or if multiple different keyboards were used across sessions, and also which features were included in the model. And I'm happy to talk more about how these factors affected performance. With that, I'm Scott, and during my PhD in neuroscience, developed new methods for studying brainwaves and burritos. Thank you.